get started this morning with a continuing coverage of our library structure. I'm going to give this talk that was originally prepared by Jared. So yeah, we're going to talk about protocols libraries 3 and 4. So starting with some of the code, we're not going to cover all of the code. Some of it we just can't cover, and some of it you'll be getting later today. So Protocols 3 lives here in the set of protocols libraries, and you can kind of see in the little choke point that it represents that there's probably a lot going on with Protocols 3. You've got a lot of complicated code, and it's all interconnected, and therefore it's not easy to split it apart into separate libraries. So it's a biggie. All right, so what's in Protocols 3? So here's a set of the top level directories. Simple moves and simple filters we'll be talking about. I'm going to tell you just a little bit about what lives in the toolbox directory, which has task operations, which you haven't been yet thoroughly introduced to. Some task operations live in core, some of them live in protocols, and some pose metric calculators. There's other code for analysis, backrub, some constraints, the FragPicker. I'll talk a little bit about the FragPicker. Loop modeling, Jason will cover this afternoon, which includes the kinematic closure code. And I'll tell you a little bit about relax. Okay, so some of the broadly useful movers that are in the simple moves directory. So one of them, the first one that's easy to highlight, Amanda?
Did you share that lecture on?
Not yet.
Yeah, I think it's really useful for people who want to take notes.
Sure, we'll get that taken care of. So the pack rotamers mover. So basically this is a mover that gets ready for a call to pack rotamers. So rather, when you create it, you're basically saying, in the future, I'd like to call pack rotamers, and then when you apply it, it calls pack rotamers. Since the apply function for movers, the interface is set by the mover base class, you get a pose. And that means if you need additional arguments for a particular piece of behavior, that has to be initialized ahead of time. So this class stores a score function constant owning pointer. That's one of the arguments to pack rotamers. It can be given a packer task to be used, or if you give it a task factory, it can create and then initialize a packer task just in time. So Jason's going to tell you tomorrow a little bit more about how the packer task works and how task operations work. But one thing I can say now is that, and Jason will reiterate it, task operations help you state in advance what kinds of things you want to do to a packer task so that you can create the packer task just when you need it and then initialize it and then use it. And then you throw the packer task away. So the first thing I should have told you was that you can only use a packer task really once. You should create a packer task just before you invoke pack rotamers, because the packer task needs to hold data that corresponds to the pose that you're going to apply it to. For instance, the packer task knows the native amino acid at each position. And so if you have like a protocol where you say do some design and then you do something else for a little while, and then in that little else section, maybe you take a moment and you just try to repack the rotamers on the sequence here, so that you may do this over and over again. You can find yourself undoing the design step in the repacking of rotamers step if the packer task that you construct there is the packer task that you constructed at the initial. Oh, sorry, the packer task that you use in that repack step. If that was the one that you constructed with your original pose, with the original sequence, then it encodes that original sequence and it puts that original sequence back on your pose. So that would be a disastrous waste of time. But again, you'll get that in greater detail. And the pack rotamers mover also has this integer end loop. So on the basis of looking at this amount of private data, can anyone guess what the pack rotamers mover is capable of doing? What does the variable end loop suggest to you? Say again? How many times it does something, right? So it's going to iterate, maybe not clear what it iterates over, but at least it's telling you that there's this option for doing something multiple times, right? Before I go on, so in fact what it does is invoke pack rotamers multiple times, or it does it in this fairly careful way, where if you want to iterate multiple times, then it will construct a single rotamer set, and then it'll compute the rotamer pair energies and write them down and save them for reuse. And then it will invoke pack rotamer, or say a subroutine within the pack rotamers function calls that just uses the existing rotamer set and the existing interaction graph to do rotamer optimization. And so it can do that several times and then take the best one and then give you the lowest energy pack structure. As you go through the simple movers directory, or simple moves directory, and maybe just generally as you look at code and try to understand how it functions, I'd recommend looking at the private member variables, getting a sense of what kind of data that class has access to, and that'll help you understand what kinds of things that mover is going to be trying to do. Okay, so the min mover, using the atom tree minimizer allows you to minimize certain regions of a pose. Okay, so again, the min mover holds a score function cop, just like the pack rotamers mover. It holds a move map, which describes how it's going to, or what degrees of freedom are free to change during minimization. Has a minimizer options object. This should feel familiar. And it has this value threshold, which I don't remember what it does, but that's one of the options. And it has a Boolean variable, Cartesian. Okay, so on the basis of this data, right, you could guess that the min mover, right, it's going to interact with a score function, right, just because you have to have a score function in order to minimize it. And maybe it's going to perform Cartesian minimization if you set this Boolean to true, as opposed to using the atom tree minimizer. One other thing that you could notice is that the min mover and then also the pack rotamers mover, they both hold constant owning pointers to a score function. Can anyone tell me why they think that a constant owning pointer would be, say, a desirous data member, or what kind of functional implications holding a constant owning pointer might have? So what is the class telling you about what it's going to do to a score function? Yeah, exactly. So it's promising not to change the score function. So if you pass it in, then it's going to use that score function and not some other score function. One other implication maybe is that if you wanted to share one score function among multiple movers, you could give a pointer to that one score function. And then each of those movers would say, make a statement about whether or not they're going to be changing that score function. Sometimes classes will hold owning pointers to data members, and that means that they're going to point to a single, like to say some external source for that data member. Sometimes it means they're just using an owning pointer for the sake of pound inclusion. This morning's lab will actually get into some of the issues of whether when you hold an object, whether you're holding the pointer to some existing object or whether you're cloning your own. And so when you make a copy of yourself, whether you should make a deep copy, whether you should clone the things that you're holding pointers to, or whether you should just copy the pointer. As it works out, both the pack rotamers mover and the min mover hold pointers to shared resources like the score function. And this allows you to do fun things like set up a score function, a min mover and a pack rotamers mover to point to a score function, and then you can change that score function and then have those movers continue to, because they're pointing at that changed score function, they're now going to respect the change that you just made. So it's a way you can sort of communicate to your movers without actually having to interact with them directly. All right, so here's another example. So the min pack mover, right? Yesterday I gave you a list of the variations on pack rotamers, the functions that live in core pack. The min pack mover does this packing operation where at each rotamer substitution step it actually minimizes the side chains. For that reason it's quite a bit slower since it's doing a lot more work. Let's see what it stores. So it stores a score function, constant owning pointer. It stores a task factory. It has some Boolean variables off rotamer pack, non-ideal and Cartesian. It suggests kind of that you can, there are like configurable options into the call to min pack, and that these variables will help you, like you can probably set them in order to choose which variant you want. In this case, the non-ideal and the Cartesian Boolean variables, they control arguments to min pack. And off rotamer pack is a completely different variation on it that you can get access to through the min pack mover. It actually calls off rotamer packing as opposed to min packing. Here's a very useful one, the switch residue type set mover. So that'll convert a pose from one residue type set to some other residue type set. So you give it the name of the new residue type set that you want, for example, centroid or FA standard, and you give it a pose, and it replaces all the residues in that pose with their corresponding residues in the other residue type set. So if you want to go from full atom to centroid, you can use a switch residue type set mover to convert your pose to centroid. The return sidechain mover is pretty fun. So this one, you give it a pose as you initialize it, and it writes down all of the sidechain coordinates. And then you give it another pose in its apply method, and it goes through and it superimposes the original sidechains onto that pose. Right, so that's super useful in docking, where you start off and you have, say you have the unbound complex, and you have maybe the original side chains that were present, say these two undocked crystal structures that you have, and you're trying to figure out what dock structure. So the first step is that you initialize the return sidechain mover with the original pose, and then you run, say, low resolution, like centroid mode docking, and it figures out how it's going to try and place these two chains with respect to each other, and then it superimposes the original side chains onto this new structure, this return sidechain mover. And so if you have a protocol where you're going back and forth between centroid and full atom mode, this is a useful mover to have. They're the backbone movers, which are declared in backbone mover.hh. So for instance, the small mover, which derives from backbone mover. It picks a random residue and then randomly perturbs the phi and psi dihedrals for that residue. Does that sound familiar to anyone? There's the shear mover. So this one, it also picks a random residue. It picks a random perturbation. So it's going to sample from a Gaussian, and it's going to change dihedral angles by some random amount x, and then applies that perturbation such that it changes phi by x, and then it changes psi by negative x. And this has the result of kind of minimizing the amount of downstream distortion. So psi is going to kind of accommodate the change in phi. And so it's an attempt at a very local move to the structure. There's the fragment mover class, which actually is a base class for several derived classes. So it inserts fragments into a pose. So we say fragment insertion. It took me a little while to understand what it meant. But what a fragment is a list of dihedral angles, phi, psi, and omega, for a stretch of residues. And we say fragment insertion, we just literally change, so get some pose over here, we just literally change the dihedral angles in that pose to reflect the ones in this fragment. And so if your pose looked like this, and then you inserted a fragment that kind of had a little downstream or like a little bend to it, then you might have that change propagate through the rest of the conformation. All right, so how does this work? In fact, the fragment mover, it contains a fragment set. You can look at, see where this class lives in core fragment. It has a move map, so it accepts from the user some description of where it's allowed to make fragment insertions and where it's not allowed to make fragment insertions. It has an insert map. I'm not sure what that is, but from the pound includes, you can go and find out what that is. It has an insert size. I'm not entirely certain what that is either. So this fragment mover class is a parent class to the classic fragment mover. And then classic fragment mover is a parent to the smooth fragment mover. Smooth fragment movers are kind of fun. So what they do is figure out for each residue. So rather, when you select a window in which you're going to insert your fragment, say I'm going to start inserting a 9 mer at position 18. So it's going to change 18, 19, 20, and down through 26. Then what it does is it looks at all the fragments that start at position 18 in the fragment set, and it figures out which one is going to have the least perturbation effect on the rest of the structure. So it's going to try to choose the best fragment given the current structure. And it does this by computing a cost based on the existing fragment that starts at residue 18 to residue 27. It compares that fragment, that stretch, with all of the other fragments. And then, so there's a couple variations on this cost. One of them, I think the only one that's implemented, is the gun cost. And you can find implementations of that in the, I think in core fragment. Okay, so let's continue. So there's a torsion DOF mover. So this one's kind of fun. So yeah, Joe.
The smooth fragment mover with the boot model, or just add a shield?
So you can use any mover kind of in any context. Like if you were creating your own loop modeling application, then you could use the smooth fragment mover. You could invoke it. You just have to create the appropriate inputs for it. You'd have to be able to initialize it. But that's totally within the realm of possibility. The torsion, so back to the torsion DOF mover. So this class, you give it a particular DOF, a particular torsion that you want to change, and it makes a perturbation on that DOF. I think that's supposed to say a particular torsion, not TO. So part of its behavior is that you can optionally test that the energy for that DOF doesn't increase, and that So what it does is it tries to find a perturbation where it computes the twist energy for that torsion, and then uses a metropolis accept or reject criterion. So the ramping mover is a pretty fun one. This one is one that you could say use in tandem with the min mover and the pack rotamers mover. So how does it work? So you ramp a weight from one value to another over n iterations, calling a mover at each iteration. It's not the whole story. So let's take a look at what it stores. So stores a score function OP, right? So it's not making a pledge that it's going to leave that score function unchanged. It's going to potentially, in fact, I'm telling you it's going to change the score function. It holds a Monte Carlo object. It holds some mover, right? Some generic any class, right? And it holds two energy maps. These again are vectors of, or they're arrays of real values where each position corresponds to a single term in the energy function. So you have the starting weights, you have your ending weights, and then you have a way of ramping between the starting and ending weights. And so there are functions that you can use, ramping functions, to describe how you would ramp over a set of weights, or over a set of iterations. So what do I mean by that? So one very easy ramping function would be linear, right? You just do a linear interpolation from the beginning weight to the end weight, where each step you're going to take depends, rather, each increase to the weight or change to the weight as you go between them depends on, say, the number of iterations that you're going to have. You could have more complicated ramping functions like a sigmoid function or something like that. Or you could have one that starts up really high and goes down low for a moment and then comes back up. Your imagination is the only limit there. And then it has two integers, two unsigned integers, outer cycles and inner cycles.
Is this how, can you ramp temperature in here for a Monte Carlo object?
So Joe asked, can you ramp the temperature from Monte Carlo object here? The ramping mover doesn't ramp temperature.
You said it does?
Does not, yeah. But that's an interesting idea, to add that functionality to this mover. Right, so the way it works is that it has an outer loop, and in each iteration of this outer loop, it's going to change the score function. It's going to change the weights. And then in the inner loop, it's going to call apply on the pose for the mover that it has. So it's given a pose to begin with, and it's going to change that pose or call apply on that pose using this mover that it uses or that it holds in each iteration through the inner loop. So you could ramp over 5 steps and then have in the inner loop maybe 100 iterations. So you're just applying this mover over and over and over again. Yeah.
So currently, do you have to just call different Monte Carlo objects with different temperatures to essentially ramp? Is that how that's handled in Rosetta now?
Excuse me. There are lots of ways you could go about ramping temperature. Excuse me. The Monte Carlo object lets you change its temperature. So you can use a single Monte Carlo object and change the temperature in a for loop, right? So you don't have to create a new one in each iteration of the for loop. I like your idea of adding a temperature ramping option to the ramping mover. Okay, so one of the reasons that I bring this up is that, okay, so the ramping mover, it's got this score function that it's going to change. If you set things up correctly, you can have the same score function being used by the ramping mover as by the pack rotamers mover and the min mover, so that those two movers see the change that the ramping mover is making. Even though the ramping mover doesn't know it doesn't know what lives inside this mover object, right? So this mover object, for instance, if you wanted to have both a pack rotamers mover and a min mover invoked in this loop, then you would have, say, a sequence mover that held each of these. So sequence mover holds it holds a vector of movers, but in this case, I'm imagining it holds one pack rotamers mover and one min mover. And so every call to the sequence mover apply calls pack rotamers mover, and then it calls min mover. And then you'd give that sequence mover to the ramping mover, and that would be the mover that it holds. The ramping mover is going to change the score function, and that communicates this change effectively to this anonymous mover inside. The way the Monte Carlo object works is that it has its own idea of what the score function is, and so if you change the score function, you need to communicate that change to the Monte Carlo object. So the Monte Carlo object has its own guarantees on what is the meaning of the last accepted pose and what is the meaning of the lowest energy pose. And that's tied closely with the score function that you use. So it doesn't, even though it holds a score function owning pointer, it doesn't have the same copy semantics that, say, the pack rotamers mover does. It has its own copy of the score function. It doesn't let you change its score function without telling it that it's changed. And so the ramping mover, every time it changes the score function, it has to notify the Monte Carlo object. Now this can be the same Monte Carlo object that the mover or the sequence mover or whatever some nested mover inside of here is using. And that way you can communicate this change to the Monte Carlo object to these movers as well. Yeah?
Re-implement that by just wrapping the other movers in Monte Carlo movers?
Well, you might want to have have a lot of Monte Carlo steps, right? You might want to. So, let's see. We didn't cover this in Protocols 1, but there's a mover form of the Monte Carlo object, which is the trial mover, and it basically calls like some move, and then it applies the Monte Carlo accept or reject decision. So that would be the equivalent form of that. But if you wanted to have like thousands of iterations through, say, phi-psi perturbations before you considered a single pack rotamers move, then maybe you'd want to have each mover kind of interacting with a trial mover independently.
Andrew, one more question.
Yes, Joe.
Can you ramp constraint weights with the weight ramps?
So Joe's question was, can you ramp the constraint weights with the ramping mover? And the answer is yes. So you can ramp any weight with the mover. You can ramp. Right. So if you you have two sets of two weights. You have two weight sets, two vectors of weights. If you want the weight to stay constant, then you just put the same value for the start and end weight. So FA attractive, you usually don't ramp that. So that would be like, say, 0.8 in the start weights and 0.8 in the ends weight. But a very common thing to do is to ramp the repulsive weight. So say in the relax protocol, which I'll get to in a few minutes, it starts with a low repulsive weight and then increases it over time. So you could mimic the relax protocol by having the ramping mover start with a low FA rep weight and then end with a higher FA rep weight. But if you want to do something like both ramp up the FA rep weight and ramp down the constraint weight, then it's nice to have this very general framework of being able to ramp any weights between any values. Right, so a mover reply is called in the inner loop. Yes.
Can you ramp the size of the moves that a mover makes?
Can you ramp the size of the moves that the mover makes? I'm gonna. There's no way that I know of to do that.
You mean like, so like if you were to set some like some possible range of numbers for movers?
Yeah, and then maybe decrease that.
Yeah, it depends on the mover. Some movers have options where you can construct with like a specified buffer and make that larger or smaller if you want to make larger more moves. It really depends on the mover. Some you can.
So with the ramping mover, because the ramping mover just stores a mover OP, it doesn't know about the internal details of the mover. So therefore, if there's mover-specific options to change the step size,
That
the
would be.
ramping mover would be able to know about it. In order to change that step size, you would need a mover that knows about the internals well enough to be able to change, modify the mover with the step size change.
Right. So for the people at home, Rocco just said that one of the drawbacks of, say, the ramping mover is that it's unaware of what's going on in the internals of its movers, and so it can't do custom things. Okay, so moving forward, let's see. There's the constraint set mover. This is a useful mover if you want to have a protocol that at one stage has some constraints and then at a later stage has no constraints. And so what it allows you to do is set the constraints early in the protocol, you can have a mover that sets the constraints. You have the same mover that also removes constraints. And there'd be different options whether it's going to set or remove the constraints. There's a superimpose mover, which allows you to superimpose the parts or the entirety of two poses. And so it takes as input a description of how to perform that or what the correspondence should be. And these, one thing to worry about is that these poses have to have the same number of atoms as you're doing the superposition. As a subdirectory of protocol simple moves, there is the symmetry directory. And within this directory, you find all kinds of useful variations on the simple moves, but that are specific for symmetry. So one of the most useful ones is going to be the setup for symmetry mover, which takes a pose, an asymmetric pose, and it makes the modifications to it that it needs to in order to make it a symmetric pose. So it's going to replace the conformation object that the pose holds with a symmetric conformation object. It replaces the energies object that the pose holds with a symmetric energies object. Okay, then there's quite a few movers in here. I'll highlight two. There's a sim pack rotamers mover that calls a symmetric version of pack rotamers and does some things to ensure that the packer task is correctly set up for symmetry. Similarly, there's special things that you have to do to a move map before minimization can begin on a symmetric pose, and the sim min mover handles that. Oops. Okay, so mirroring the protocols moves directory, there's a protocols filter directory. We haven't talked about this yet, but so protocols filter has a couple key functions. The main one is this apply function. So you give it a constant pose, and it will return true if some condition is met, and it will return false if that condition is not met. And this is often used to gate progress through a protocol. So you're going to run, say, a long design protocol, say a protein interface design protocol. In the first step, you're going to take two proteins and you're just going to jam them together, and you're going to take a look at the resulting Doppler conformation. And maybe you want to make sure that the size of the interface that you produce is big enough to make it worth going into the design step. And so you might have, a DSASA filter, right? So if the interface is just like glancing like this one, then maybe you go ahead and reject that structure, you start over, and the protocol begins anew. So filters are one of the main components of Rosetta scripts. There are filters and there are movers. And in Rosetta scripts, if you ever fail to pass a filter, then the Rosetta script starts over at the beginning. So that's handled with this apply function. The other thing that filters have, the other function that they've come to take on is actually, yes, is there a question?
Yes.
Alex.
Can you set the filter such that instead of like passing some hard threshold, like say if you're doing some design round, can you set it so that it only passes filter if it improves in the previous round? So it's kind of very
So the question was, can you have the filter get increasingly stringent by recording what the decision was of a previous round, so that things just get better? That's an interesting idea. The short answer is no. And the reason is that when you apply a filter, you're not supposed to change that filter. So the filter's apply function is const, so it's not supposed to change as a result of seeing a pose, of making a decision. Yeah, I'll just leave it at the short answer. The other thing that a filter does is that it can actually report a value. So if you give it a constant pose, it can actually compute some value, some real value, and then return that. And so often people will use their filters as a way of actually diagnosing or analyzing the structures that they're producing. And so sometimes you'll see a filter used even when you're not applying it. You're not trying to get the Boolean pass-fail condition. You're just trying to get at a particular value. And the name of this function is report SM, and I cannot tell you what SM stands for. Anybody else have any idea? SM?
I think it's score metric.
Score metric. Wouldn't have been a bad idea to type that all out. Yeah. Okay, so let's see. So there's some common subclasses of filter. For instance, there's a score cutoff filter. Is the energy of some pose lower than some cutoff value? This has to be set up when the filter is initialized, right? It can't, as Alex maybe hoped would have worked, it can't increase its stringency as time progresses. There's a score type filter, and that's a way of saying, is the energy of the pose for one particular term lower than some threshold? Maybe you want to make sure, is it lower, or maybe is it higher than some cutoff value? For instance, maybe you want to make sure that the FA repulsive weight is below 100 or something. Maybe you're just not going to bother with structures that are in terrible collision. I encourage you to poke around in the simple filters directory to see what other options are available. Okay, so just a few notes on this directory toolbox. So it's fairly generic. It has a lot of things that are kind of mishmashes of pieces of functionality. This is a great place to go and find things that you can use in your own protocols. And people have put code here. They put it high up in the protocols library instead of down low so that other people can have access to it without introducing strange cycles in the dependency graph. So one thing that lives here is a set of task operations. The thing to note is that some task operations cannot live in core 4 with the rest of the things in the core pack directory. And that is because they depend on other code in the protocols library. And so there's some task operations that live down here. I'm not going to go into what these are, but you're welcome to take a look. There's a set of pose metric calculators. So we haven't described this in our tour through core, but there are these things called pose metrics that lives in source core pose metrics. And the pose metric base class, like its purpose is to compute some fairly difficult to compute value and then cache it so that if you have a couple of steps that all need to know what the SASA is of a pose, and SASA is a little expensive to compute, then you have this pose. The pose metric will report the SASA, and then so long as the pose doesn't move, then that SASA that is computed will remain unchanged, and so you can get it fairly quickly. So it's a way of saving some computations. The two major flavors, there's the structure-dependent calculator, say it's SASA, there's an energy-dependent calculator, and there's some useful pose metrics that live in this protocols toolbox pose metrics directory. Okay, so one of the protocols that I think almost everyone is likely to use at some point or another in their graduate career is going to be the relax protocol. And so the idea of relax is just to take a structure and to move it ever so slightly, maybe just within an angstrom, maybe an angstrom and a half of its starting position, so that you can find a local minimum or a very deep minimum that's nearby. So relaxation attempts to find a nearby or low energy one of the nearby energy minima, and it samples confirmation space more thoroughly than, say, just a minimization would do. Okay, so there are three main flavors. There's classic relax, which has been around for quite some time, and it's contrasted with the next one I'm about to show you, FastRelax, because it spends more time making small perturbations to the backbone and then minimizing in response to those perturbations. It's not recommended. The new flavor of relax, FastRelax, is less effective in each run. It's not going to get as low of an energy in each single execution of the protocol. But in the time you save, you can actually run it several more times, and searching several independent trajectories of FastRelax is a better use of your time than just with a single iteration of classic relax. So FastRelax and classic relax before it had this, excuse me, not temperature schedule exactly, but tolerance to van der Waals collision. So you start off and you're extremely tolerant of van der Waals collisions, and then over time you become less tolerant. And the way this is implemented is by tweaking just the weight on the repulsive component of the Lennard-Jones term. So over time, the repulsive weight increases. The final version, centroid relax, I don't believe it is yet online, but it's something that the Baker Lab is working on. Okay, so what does FastRelax look like? So it's a pair of nested loops. In an outer loop, you're going to go through some number of cycles. This is an example of 5 cycles. And then in the inner loop, well, just before you begin the inner loop, you set the FA rep value to some low value, for example, 1/10 of its original weight. And then you ramp this weight up. So you're going to ramp over a series of steps here, 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 here. And in that, in this loop, you increase the FA rep weight, then you repack the structure and minimize. And that's it. So it's a very small protocol in terms of complexity of the subroutines that it's invoking, just repacking and minimizing. It has this, so yeah, you start with a low repulsive weight, and then you increase it, and then you write down the energy of the structure that you get here. Then you start over again with a low repulsive weight, increase it, and write down the best energy here, or the energy that results. And then at the end of the protocol, after your 5 iterations through the outer loop, you just take the structure that had, say, the lowest energy, and that's the one that you're going to return. So one effect that having this low repulsive weight one effect of it is that at the beginning, minimization kind of pulls the structure in, and then over time it kind of like lets the structure go out. And then you start over again and it pulls the structure in and then it grows out. And so if you look at a movie, which I didn't have time to generate, of what happens to a pose over the course of relax, it looks like the structure is kind of breathing, kind of like inhales and exhales. And this is a fairly effective way to kind of like relieve collisions and then say let two rotomers slide past each other to find a lower energy. Okay, so one thing that Jared wanted to point out is that the minimizer type that FastRelax uses is I don't think it's this one. DFP-min, Armeggia, non-monotone. There are actually several flavors of minimizers. I think the current one that's recommended is this LBGFS, Armeggia, non-monotone, and I think you were using that in lab 2. Sorry, I should have taken a closer look at that yesterday. There are a couple variations on FastRelax. You can do it using internal coordinates, using the atom tree minimizer. You can also use a Cartesian minimization. And so there's a variation where you can just do Cartesian minimization. And then there's this one called dual space, which does a combination of Cartesian and internal degrees of freedom. It actually does it in reverse order. So it starts in internal degrees of freedom, and then it goes to Cartesian minimization toward the end of the protocol. And Patrick Conway and Frank DeMaio have found that this is a good use of time to get very low energy structures. I think we don't cover this in the lab, but if you're going to do Cartesian minimization, then you have to have the cart bonded term on in your score function. And you also have to have the pro-closed term off. And so if you want a variation on the Teleris 2013 weights that you can use for Cartesian minimization, that's in this weights file. And Jason in his tour of the database will probably tell you where this weights file can be found. He's going to do that tomorrow. Okay, so also in Protocol 3 is the fragment picker. It lives in the FragPicker directory. So fragments are a way that we can quickly sample locally consistent low energy backbone conformations. And so we usually have fragments ranging either from 3 residues, that's 3 Phi Omega triples, or to 9 residues. 3 residues is good for really optimizing and tweaking a structure because it's just making just very small changes generally to a structure, or it can be used to make very small changes. 9 residue insertion or fragment insertion tends to move the backbone quite a bit, and so it's a good way to explore a wider region of conformation space. Okay, so how do you get fragments? Well, they're selected reflecting local sequence properties, but based on secondary structure or the predicted secondary structure, and that takes into account, say, the global, the sequence that's given for the entire stretch of the protein, right? So based on the entire sequence alignment, you figure out what the sequence, the secondary structure will be for a particular region, for a particular stretch, and then use that information to pick fragments for that stretch. Okay, so programmatically, so how does it work? Well, it scans through fragments from the PDB, which we refer to as the V-all, as opposed to vol. It's V-all. And so these are Phi Psi and Omega values from idealized structures. So we work principally in internal coordinates and principally in dihedral angles. And so that means that the other degrees of freedom, the bond lengths and the bond angles, those are held fixed at some idealized value. So if we're going to use the dihedrals from the PDB, people have to first idealize the PDB. So we change the bond lengths and angles of those structures so that they're what we expect them to be. And then we write down the resulting dihedral angles. So you take a fragment, that's this window of 9 residues, and then you're going to keep, say, the best 200 fragments. I'm sorry, So each fragment corresponds to a window of 9 residues. And for each window, you're going to keep, say, the top 200 fragments. And there's a couple ways of ranking them. So you can have some score function, and then take just the top 200 from each in the score function, or as determined by the score function. You can also have some idea of like uncertainty in your secondary structure prediction. And so you can hedge your bets by saying, okay, well, my secondary structure prediction told me that it was like 30% likely that it'd be helix and 70% likely that it'd be sheet. So I want my fragments to respect that and give me 30% helical fragments and 30% sheet fragments. So you divide your fragments into which secondary structure they represent, and then you pick the best within each secondary structure group. So this is called the quota routine. And the fragment picker is available either programmatically or through the fragment picker app. Just to give you a little glimpse of the internals, it has a fairly generic and extensible way of describing how you should score each fragment. So there's a fragment scoring method, and there's and this is the base class from which a number of fragments derive. For instance, the sequence identity, which would say compare the sequence at your protein, your target protein, against the sequence that your fragment has originated from. And that would give you some score. And then you can integrate scores together in some weighted fashion, and then the total scores is how you would rank fragments. And for computational efficiency, there's a subclass which is this caching score method, which can store per residue data about each of the residues in the protein, and then that can be reused as you slide the window across it. So each residue in each protein in the PDB, if you were selecting 9-mers, it would appear in 8 different 9-mers, right? Or 9 different ones, right? And so if you have some per residue data that would contribute to each of those 9 fragments, then you can compute that a little bit more efficiency using this caching scoring method. Generally, the way people interact with the fragment picker is through this through the executable, the FragPicker application. And of this, the most, I guess the best way to do it is to use this make fragments .perl script. This lives in the Rosetta tools repository. If you want to make fragments on your own computer, it is a challenge. And Jared offers this advice. It's not for the faint of heart. Go have a beer. And I'm not sure whether what he means is that if you are faint of heart, you should go have a beer. Or if you're going to do it, you should reward yourself for having a beer. But I think really what he means is that anyone who's thinking about it should probably go have a beer. Okay, what you'll need. So you need the NC/BIC toolkit, and our BLAST database, Cypred, SAM, Predict Second, JUFO, Porter, and their instructions on the wiki. And these are apparently difficult to install. Okay, I can't tell you anything more about these, but maybe Jared could. Right, so once you get these tools compiled, and in the case of SAM configured, then you'll need to edit the make fragments script on your machine to point to those executables, and then if you have trouble along the way, you can always use the Rosetta server. Just for the people at home, this is accessible only to academics and not to industry people because of the licenses with some of the software that's on this server. Okay, so One mover that is pretty cool if you're doing, say, protein interface design or protein-protein docking is this interface analyzer mover, or IAM. And it looks at protein-protein or protein-ligand interfaces and calculates a variety of metrics. And for each metric, there are actually a couple different ways of considering that metric. So, for instance, it'll look at the interface energy, that's some DG bind, and it can calculate it either as just the two-body scores across the interface, which might be one intuitive way, like what's the FA attractive score for all the contacts across the interface. One way, say a different way would be to separate the two partners and then calculate the interaction energy as the difference between the complex energy and the separated energy. This addresses some of the issues with, say, context-dependent energies. Yeah, to a certain extent. No, never mind. So, for instance, hydrogen bonds are stronger when they're buried, and so when you separate the interface, then the hydrogen bonds, say, the intramolecular hydrogen bonds will get weaker as a result. A final way would be to, again, separate the partners and then to allow the side chains that were at the interface to repack, to relax, say, away. So if you have this methionine that's say, laying down across the interface so that the other partner can come by, then when you separate the partners, this methionine could adopt a lower energy rotamer by relaxing into another conformation. So that would, so between these two, you can imagine there being a bias towards energies looking better according to this metric than this metric. This metric is only going to lower the energy of the separated complex and therefore make the gap between them seem smaller. The interface analyzer mover will also compute the change in SASA, again, using something similar here where you have the SASA to begin with, you take it apart and you recalculate the SASA, and then that can tell you how much solvent accessible surface area has increased or decreased as a result of the complex formation. And one thing that we in the Coleman lab often look at to analyze the quality of our interfaces is this ratio of the DG bind energy to the d-SASA area, and we call this the binding energy density. It's how much energy are we getting out of each square angstrom of buried surface area. These aren't the only things that the interface analyzer mover reports. It's just a subset, and so I encourage you to take a look at what that code looks at. There's a similar version for loops. There's a loops analyzer mover, and it looks at the loop quality and then how well the loop has been closed. So remember from your fold tree lab that often when you're doing loop modeling, you insert a cut point in the center of a loop, and then you have to try to close that cut point. You have to make the residues on either side of it respect, bond distances and angles. And so this mover can help you get a sense of how closed or how low energy a particular loop is. Yes, Tina?
So what is the range of bounds you get for your binding energy? Isn't that like it's very similar, like per square?
Yeah, it's, I believe,
Is the DG that you calculate good enough when you try? What will it be?
yeah, we have a good sense that the distribution of binding energy densities of relaxed interfaces from the PDB, if you were just to plot binding energy versus size, you would see a fairly close or a very high correlation. So that if you were to plot by size on the x-axis, the binding energy density, it's almost a constant. And so we aim to have, so that constant is, I believe, 0.015 Rosetta energy units per square angstrom. And we often look at it multiplied by 100 because it's all the zeros out in front they just obscure what you're looking at. Yeah, I think we have a plot of that in this old paper. I can point you to. Another way of modifying structures is by performing normal mode variations where you, I guess, maybe you run a little MD first and get a sense of what the principal components of motion are, and then you can sample the protein motion along those principal components. I didn't look into this in great depth, but it's here, and I think it sounds pretty cool, so I'm going to look at it later. I encourage you to as well. All right, so that concludes Protocol 3. Can somebody give me a sense of the time?
9:37.
We started at 8:30? Yes, a little after 8:30. Okay, so let's talk just a little bit about what lives in Protocols 4. This is more of what remains of the presentation is like, this is code that exists as opposed to this is how code works. So we're not going to go nearly into the depth. So there's docking lives in Protocols 4, ligand docking lives here, motifs, grafting, domain assembly. The membrane code that Rebecca is working on lives here. Floppy tail is a very widely used application. Comparative modeling, and then I'll close on optimized weights and multi-state design. Okay, so the code that lives in Protocols docking, this is historically this has been developed out of the Gray Lab, though there's been great contributions from or by Chu Wang and Ora Furman from their time in the Baker Lab. Docking is canonically divided into two parts. You have a low resolution centroid mode phase where you say if you're doing global docking, you take your partner, you spin one of them randomly, and then try to bring them into contact. I guess you can spin both of them. And try to figure out what's just based on rough shape complementarity, what's a good docking orientation. And you take that centroid mode structure, you put that through a high resolution phase. So the code reflects this two-stage protocol. There's a set of low resolution movers, docking low res, and then there's a high resolution mover or a couple of variations on it, such as the docking MCM, the docking Monte Carlo with minimization protocol. And these two together are mostly used by the docking protocol class, or that's how I think you're probably most likely to use this code, is by creating a new instance of docking protocol and then configuring options within it. It's possible to run docking, redocking on a structure if you just want to refine it. Let's say you've got a candidate interface and you just want to wiggle it around a little bit to see if there's some low energy minima in the vicinity nearby. And so it's possible to disable, for instance, through the docking protocol mover, the low resolution step without having to construct your own high resolution mover. The ligand docking code, there's an older version that's available through the command line application. I think it's called ligand docking. This one has been deprecated. Instead, the current line of development is through Rosetta scripts, and it's coming out of the Milo lab. And so there's a wiki page where you can find a description of it. So there are low resolution movers. There's transform, translate, and rotate. And they use this low resolution Cartesian grid, which sort of maps out what the protein looks like, and then try to place the ligand first in the binding pocket in some somewhat reasonable binding orientation. And then that's followed by a high resolution stage where you have this high res docker that alternates between rounds of packing and rotamer trials and minimization. And then there's a final minimizer, which I guess does some amount of backbone and ligand minimization as well. The code in protocols motifs is used to impose motifs onto backbone scaffolds using an inverse rotamer approach, that is building from the ligand and through the contacts that the ligand is going to make with the protein back to the backbone that needs to come from, and I think to then remodel and design the backbone to accommodate these rotamers. I can't tell you much about the code except that it lives in protocols motifs. And I can point you, though, to this paper here from the Havranek lab. The grafting code comes from Stephen Lewis and Jared, where you try to take pieces of a protein and move it onto another pose using various modeling strategies, including CCD loop closure algorithm. The main class is this anchored graft mover, which Stephen originally developed, where you would say, this is used in protein interface design, where you have a motif that you would find, say, from your target interacting with a peptide maybe, and you want to graft that peptide onto some scaffold protein, so that then the scaffold with this peptide will then bind to the target. There's some useful functions in here, including deleting regions from poses, returning or selecting regions from poses, replacing one region with another region, and inserting one pose into another pose. There's some code in the domain assembly directory, which is used to try and predict the not tertiary, but quaternary contacts between two domains. So if there's some flexible linker between two domains, and you have the crystal structure of the two domains, what is the final structure going to look like? There's some code that's actively under development by Rebecca and Julia Lemon in the Gray Lab for modeling membrane proteins. They're not the first people to work in Rosetta on membrane proteins, but some of their code lives here, where they're able to, say, set up a special membrane pose with this create membrane pose mover that mirrors the symmetry mover. This code is actively under development, and I'm not terribly familiar with it, so I'm going to just tell you that it's here, encourage you to look at it, and move on. The floppy tail protocol also lives in protocols 4. It models, say, the floppy ends of, say, the N-terminus or the C-terminus of a protein, and it's used to answer these questions like, I've got this tail, and I think it binds on this other side of the protein. Can it reach? Is there any way to bring this tail over to the other side of the protein? The protocol is not meant for finding the lowest energy structure for this tail, but just to answer questions of feasibility and plausibility. I can tell you a little bit about the optimized weights directory. So in here is the code for the opt-e protocol. Its idea is to iteratively tweak the weights and then to redesign structures. And the weight tweaking takes a maximum likelihood approach, where you have some large amount of data, and you ask, what is the score function that makes this data most likely? So your data could come from, say, the sequences for a set of training proteins. Like, what score function makes the observed amino acid sequence the most likely sequence? Given that same training set, you can also ask, what score function makes the observed crystal rotamers the most likely rotamers? And given some maybe set of low resolution near native structures and some low energy, high RMSD structures, you can ask, what's the score function that best discriminates the decoys from the natives? And so this code was all put together with this idea that we have a very expensive objective function we want to minimize. And so we use MPI to distribute the computation over a large set of CPUs. And then these CPUs are responsible both for performing the objective function evaluation and derivative evaluation, and then also the design step that follows it. Unfortunately, it tends to produce bad weight sets. Sometimes it will, and almost entirely it produces bad, say, just in the backbone training, it gives you bad weights on the RAMA term. It tends to put a negative weight there as if you would want a bad RAMA. I think that reflects just the choice of training examples that the Rama term is lower in energy in the decoys than it is in the natives. And so one way to discriminate natives from decoys is just to say, well, the bad Rama is good. It also finds itself stuck in local minima frequently. For instance, if you ever get to a point where you set the weight on the LJ rep term to be negative, then the next round of design, you try to design as many collisions as you possibly can. And then once you've done that, then the following round of objective function minimization has no idea what it should do in order to get a positive weight on the repulsive term again. And so then the whole trajectory is weak. Okay, so that's a big bummer and disappointment. But fortunately, once we've created this protocol that distributes design across multiple processors, it was very easy to tweak it ever so slightly so that instead of trying to train all the weights at once, you just train the reference energies. So this is the reference energies are a component of the Rosetta energy function where there's one energy per amino acid. And so if you were looking at position 15, in order to get the reference energy for that, you just ask, what amino acid is there? Is it tyrosine? Okay, then its reference energy is negative 0.15 or whatever that value is for tyrosine. What we use opd for is to train the reference energies based on iteratively redesigning a set of structures. And for this purpose, so what we do is we train to fit the amino acid distribution of the resulting designs. So if we saw 2% tryptophan in the resulting designs, and in the training set, and our resulting designs have 0 tryptophans, and that means that we need to decrease the reference energy on tryptophan so that we get more tryptophan. And using this protocol, we can get surprisingly good sequence recovery, better sequence recovery than when we were fitting both the reference energies and the weights. And we use this now all the time. So if you're interested in running this protocol, there's a paper on it, and you can email me about getting the input files as well. So let's see. The last thing I can mention is the code that lives in the packdaemon directory. This is also in core 4, protocols 4. I can't remember which of the protocols library it is. It's a multi-state design approach where you're going to distribute states, that is a protein, like a PDB, and some way of interacting with that PDB. And you can distribute that across multiple CPUs. And then the first node, node 0, is going to broadcast a string representing a sequence to all the nodes. And each one of those nodes is then going to receive that sequence and start imposing that sequence on its pose. It optimizes the rotamers for that sequence, sends back an energy to node 0, and node 0 looks at all of the energies together to come up with a fitness for that sequence that it broadcast. And this fitness depends on the design objectives. And so it might be, so the question would be, for state 1, amongst the set of states that I have, do I want that to have a low energy or do I want it to have a high energy? Sometimes your design objectives are that some things should be bad. And so then you would say the fitness is better if state 1 has a high energy. And then the fitness function can be provided to node 0 through a text file. And I mentioned in the overview of the numeric library that there's ways to read text files and turn those into numeric evaluations, and that code is used by the packdaemon. Okay, so I'll stop there.